We expect collaborative robots to be safe, but how is safe defined? And secondly, how do users test collaborative robots to see if they will be safe in a given application? As we have presented earlier, the International Standards Organization has published a technical specification, 15066, which provides a great deal of guidance for designing safe collaborative robot applications. However, to date, 15066 says very little about how to test robots to determine if they meet the safe forces described in the standard. In this lesson, we will describe how my company, Precise Automation, tests robots against the standard, and we will show the data provided to customers. Other companies may take a different approach.
That brings us to another level of technology. So along the way, the first step of anything is getting it running and getting it running repeatably and correctly. That's becoming more efficient. It's usually during the efficiency phase where folks start looking into monitoring the robot production, what it's doing, how fast it's doing it. Then that starts taking us to the next level of Industry 4.0, the Internet of Things, where robotic systems are tied to a network and there's softwares to monitor the process and report up to management, but not only take that, but report out to other systems. A perfect example is if you have a robot go down, maybe the system downstream will slow down its process a little bit or do something a little different or diverge. Maybe if the production rates are up or you start collecting data on frequent error, you keep having the same inspection error and error again. Maybe it sends messages upstream to change processing or flag that a tooling or bit needs to be changed. It's this whole interconnectivity. But that's usually, when you talk about in beginning robotics, this is usually a second step. Now, it's nice to think about it when you're designing your system, possible connectivity, but let's talk one step at a time. Spec your system right, get it running successfully, then start collecting data. Just make sure you have those hooks in there when you do.
Broadly, there are two different types of collisions with people defined in ISO 15066. Collisions in free space, which are called transient collisions, and collisions against a rigid surface, which are called quasi-static collisions. These collisions are very different and result in very different collision force levels. Here you see a robot tester stopping a collaborative robot moving in free space at 1.5 meters per second. This is a light payload collaborative robot with various design features to minimize collision forces. The robot stops in a few millimeters when a collision is detected. This certainly appears safe, but how do we really know what the collision forces are? Much of the human factor data used in developing ISO 15066 was taken at the University of Mainz in Germany. The university developed a machine that could apply both static and dynamic collision forces to various parts of the human body. Statistics were developed for pain thresholds on the usual volunteers, in other words, graduate students. Mainz developed several key measures. First, clamping force in newtons for static conditions. Secondly, impact force in newtons for dynamic collisions. Third, pressure in newtons per unit area. And fourth, compression constant in newtons per millimeter for the stiffness of different regions of the body. These measures can be used to determine the safety of collaborative robot applications. For example, while a force of 20 newtons, or 2 kilograms, might be safe if applied to a person's hand by a flat object, that same force would not be safe if it were pressing a needle into the person's hand. In this case, the pressure, or force per unit area, measure would be exceeded. Section 7 of 15066 addresses verification and validation, but not collision force testing. This section starts out by listing the documentation recommended for collaborative applications, including a description of the robot system, the application, and the tooling, along with drawings of the work cell. The specific safeguards for the application need to be described in detail. For robots that fall under the category of power and force limiting, additional documentation is recommended. This includes the effective payload, which includes the robot moving mass, the end effector mass, the payload, and the forward reflected inertia of the drivetrain, which can be quite large. It also includes the body part that could be contacted and the type of contact that might take place. Contact could be free space contact or a rigid surface collision. As we demonstrated with our needle example, not only force, but pressure must be examined for these different types of contact. Finally, risk reduction measures should be described. These might include reducing the robot's speed when approaching pinch points, wrapping rigid objects with foam, tools that break away at certain forces, and fixtures that are spring-loaded and deflect if an operator is trapped by the robot.